This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. So we can get on to now the notion of completeness. So we'll first define a Cauchy sequence. So we said that a sequence in RD is Cauchy if for any epsilon greater than 0 there exists some n such that any 2 points n and m after that point m will lie within an epsilon neighborhood. So we can see here, it can do whatever it wants beforehand, and then eventually it has to, all points have to squeeze within an epsilon of one another. We have that every Cauchy sequence in RD is bounded. And we can see an example here. We have xn, which is minus 1 to the n, is bounded, but it's not Cauchy because, yes, it's bounded between these two lines here. But if we were to take, epsilon to be 0.1, then the subsequent points wouldn't lie within 0.1 of each other. But for example, minus a half to the n, it is bounded. And it's Cauchy because eventually, after any amount of time, these points will become arbitrarily close together. Now, a convergent, if a series converges or sequence converges, that means it's a Cauchy sequence. That should be fairly obvious from the definition that if it's going to converge, if you were to replace this with its conversion point, you kind of recover the definition of a convergent sequence. So rather than it just getting arbitrarily close to its conversion point or its limit point, it'll just get close to each member in the sequence will get close together. So convergent will imply that it'll be Cauchy. And if a Cauchy sequence has a convergent subsequence, that means that the Cauchy sequence itself also converges. So for example, this sequence here is not Cauchy, so we couldn't just, as before, we showed that this did have a convergent subsequence, where we just take, 1 each time, so every even power, but it's not Cauchy, so this sequence then doesn't converge itself. We said that a set is complete if every Cauchy sequence in the set converges. And in fact, we have, you might be thinking that this just seems very similar to convergence in general. And in fact, in RD, you are completely correct. RD is complete. So in RD, Cauchy is completely equivalent to the idea of convergence. If we were to take a subset of RD, that subset is complete if and only if it is closed. And there's sort of a quick proof here because this fact didn't seem very obvious to me when I went through it. So if we first assume that X is complete, then that means that every Cauchy sequence in the set converges to some point in X, and that point is therefore a limit point of X, and therefore X contains all of its limit points. And we know that the closure of X is X union its limit points. Therefore, since these two are the same, X contains all of this. This is just X, so X closure equals X, so X is closed. And then the other way around, X is closed, well, X closure equals X, so X contains all of its limit points. If we take a Cauchy sequence in X, therefore, because it's Cauchy, it's bounded. And by Bourdon-Navier stress, bounded sequences in Rn or D have convergent subsequence. And because it's Cauchy, if it has a convergent subsequence, it's convergent, so it converges to some P, and that P must be in X because X contains all of its limit points. So X is complete. So now the last thing in this video, we'll say that that R is dense in R if its closure is equal to R. And a very common thing that comes up is the fact that the rationals are dense in the reals. And we can prove this using open subset. So if we were to take any real number x and u to be some neighborhood of it, we have that since u is open, there exists some epsilon such that we can move an epsilon to the left and right of x and stay within u, or we could actually just move an epsilon to the left and stay within U here. So since every open interval contains a rational number, and you can prove that via the Archimedean property that in between any two real numbers, you can sandwich a rational number, which should make sense. If you have two real numbers, right, the idea could just be to, if they have an infinitesimal expansion, you can just, obviously if they're very different, you just have to choose any rational number between them. But if they're close, if they're distinct numbers, if they would have to be an open interval, then you just have to write out decimal expansions until they differ, and then that's where you can just truncate the rational number and you have something in between them. So yeah, you can always pick a rational number in between two real numbers. That means there's a rational number in here, and this is a subset of U. That means that U, which is the neighborhood of X, intersects the rationals at some point other than X. So that's the definition of a limit point. X is a limit point of the rationals. And we can write out what the closure of the rationals is. It's just rationals union all its limit points. But we have that X, which was some random real number, was a limit point. So that means every real number is a limit point of the rationals. So that means that the limit points are just R, so it's just Q union R is its closure, or rather just the closure equals